discussing very important characteristic of the control system, which is time response of first order system. So in a time domain analysis, the response of a dynamic system to an input is expressed as the function of time. So whatever the response of the system, suppose this is RT must be equal to FT, and it can be, you can say it can be linear function AT plus B, it can be parabolic function AT square B, and it can be anything. So the time response of the dynamic system is maybe represented as the function of the time. So it is possible to compute the time response of a system if the nature of the input signal and the mathematical model of the system is known. So over here, what I am writing for the response of the system, maybe the response of Ft with respect to certain input. So this input should be known to us, as well as the characteristic or mathematical model of this particular function is also known to us. So usually the input signal to control system are not known us fully ahead of time. So it is a quite challenging job to model the certain practical systems in a fully manner, but partially we can do, and we can present an analysis. The best example of this is a radar tracking system, because the position and the speed of the target to be tracked may vary in the random function. So it is not actually known. So it is therefore difficult to express the actual input signals mathematically by simple equations. Here, the standard test signals we will be discussing. So the characteristic of actual input signal can be a sudden shock, a sudden change, a constant velocity, and the constant acceleration. So the dynamic behavior of a system is therefore judged and compared under application of certain standard signals like impulse function, step function, constant velocity, constant acceleration system. So these bunch of signals are actually known as the standard signal. One of the standard signal is it is of great importance, and it is known as sinusoidal signal. Here we are defining some standard test signals like impulse signal. When there is a sudden increment in the input and the remain time input is actually it is equal to 0. So I define that for t is equal to 0, the magnitude of the input signal is A, and for remaining time, the signal is actually is equal to 0. So this is a kind of sudden shock which we are observing. When the value of this A is equal to 1, we call it a unit impulse signal. Here I am showing standard test signal like step signal. Whenever the value of the input signal is A, when t is greater than 0, then I call it a step signal. And whenever this is actually, you can say, whenever the t is less than 0, it is actually 0. If the value of the A amplitude is equal to 1, we call it unit step signal. Now we see the ramp signal. The ramp signal imitate the constant velocity characteristic. So here I define the position vector is equal to AT, which is shown over here. So when this position vector is constant for t is greater than 0, I can say this is the ramp signal. And when this value of A is equal to 0, A is equal to 1, we call it it is a unit ramp signal. So what is R is equal to AT? If I differentiate it, dr by dt is equal to A, and it is constant. So this dr by dt is nothing but the slope of this curve. So slope of this curve is actually constant. If I want to calculate the ramp with slope A and ramp signal with unit ramp signal, so when I calculate this, let me see, this is A point, this is B point, and if I calculate the the slope of this particular signal, I can write y2 minus y1 by x2 minus s1. It is actually 1. So the slope of this particular function is equal to 1. Now somehow we can also define the parabolic signal. So this parabolic signal is what? When t is greater than 0. The value of this is AT square by 2. So the slope is not actually constant. So the position is what? Position of any point is given by this expression. So AT square by 2. If I calculate dpt by dt, it is actually varying. That means at every point, if you calculate the slope is varying. So for this signal, slope is varying, and it is varying with the time. 280 by 2. That means the slope of this particular part, yani ki m, If m is the slope, it is 80, and this slope is actually proportional to t. However, if I take double derivative of this d2p t by dt square, it is actually constant. So this is a unit parabolic signal. So this parabolic signal with slope a and this parabolic signal with slope 1. So when this value of a is equal to 1, I call it unit parabolic signal. A is equal to 1. We call it unit parabolic signal. Now, if I define the simple relationship delta t, ut, rt, and pt, I can say that impulse is when t is equal to 0, impulse is this. Step signal when t is greater than 0, the value of a is this. And if I say ramp signal, so if I differentiate this, I will get this. If I differentiate this, I will get this. If I differentiate this, I will get this. So that is how I show you. And vice versa, if I integrate it, I will get this. If I integrate it, I will get this. And if I integrate it, I will get this. So this is how these standard test signals are actually interlinked with each other. So I can say the parabolic input is the integration of the ramp signal is integration of the step signal is integration of impulse signal. Now, Laplace transform, if we can see that the Laplace transform of this particular signal, impulse signal, is equal to A. Here is Laplace transform of the step signal is equal to A by S. If I say unit impulse ramp signal, it is 1 by S square, and this is 2A by S2. Laplace transform of the step signal. Now, time response of the control system. Time response of a dynamic system response to an input expressed as a function of time. So here we are giving some, you can see step input, or you can say impulse input to the system, and what we are getting the response of the system like in this manner. So the time response has two components. One is the transient response over here. This is the transient response, which is actually having oscillations. And another one is the constant response. This is called steady state response. So when the response of the system is changed from rest or equilibrium, it takes some time to settle down. So transient response is nothing but the response of the system from rest to equilibrium to steady state. So the intermediate state, when the system is perturbed from its operating equilibrium, and again when it is reaching the operating equilibrium. So suppose if I draw the transient state of any voltage signal, if I say this is the unit value S, that represent the steady state, and if you say my signal is like this, so this is actually again it is operating on S. So this period when the value of this particular signal is actually observing some perturbation until it achieves the operating equilibrium is called transient state. So time response of the system after the transient response is called the steady state response. Here you can see one of the response of the system. Now this is also when it is having the steady state value till here. This is the transient response. So transient response is between this 0 to 16 seconds. It is a transient response, and beyond that it is a steady state response. Now, if we say the time response of the control system, transient response actually depends upon the system poles only and not type of the input. So this is very important part. How the pole of the system is actually located, the transient response mainly depend on that. So it is therefore sufficient to analyze the transient response using a step input. So always we do in labs also we have done step input. What we do, we choose a system, we construct a transfer function, and then what we do, we do the step response analysis. So every time we do the analysis with respect to step response, because the transient response only depends on the system. That's why. Although we can do it on many type of responses, but it is not actually worthwhile to conduct this analysis, because our concern for the transient period is mainly the location of the system. However, the steady state response depends on the system dynamics and the input quantity. That is why. So it is then examined during different test cycles. So from here in this slide, I give two information. So the time response analysis actually can be divided into two parts. First is steady state analysis, which entirely depend on the input of the system. And second part is transient analysis that depend on the system poles. That's why we are not very much bothered on the size of input, type of inputs. Now let us see one first order system which is having only one pole. So this is the standard form where K is known as the DC gain. So this is what DC gain, and this is what time constant of the system. The time constant is a measure how quickly first order system responds to a unit step input. That means the value of this T is actually very crucial whenever we are observing the system. If suppose this is a system and I observe this system with respect to a unit step input. So this is a unit step input which is given to it. And then if I'm observing the transient response of that, suppose this is the transient response, then the characteristic of this particular model, mathematical model, that means the system poles are actually quite crucial for judging the transient response of this. DC gain system is nothing but the ratio of the input signal and the steady state value of the output. So if you see this example, here DC gain is 10 and the time constant is 3. So this is the standard form where I write K upon TH plus 1. So this K is DC gain and T is the time constant of the system. Now for following system, if you say this is now converted into standard system, that means 3 by 5, 1 by 5 into S plus 1 and computed K T S plus 1. So this K is equal to 3 by 5, that means 0.6 and capital D is equal to 0.2, which is I have written. So this is how we calculate the DC gain of the system and the now impulse response of the first order system. You just see how we are calculating impulse response. So impulse response is what? If the value of the input is equal to 1 unit impulse response at t is equal to 0 and for the rest of the time it is equal to 0. So this Rs is equal to 1. Now what we do, Cs is equal to K Ts upon plus 1, which is actually Rs, Ch by Rs. Cs is equal to this. Now if I rearrange this, I can easily write this Kt and S plus T. Now in order to represent the response of the system, we need to compute the inverse Laplace transform of the above equation. So when I calculate the inverse Laplace of this, I got that this response of this particular system is like Ct Kt e to the power minus T by T. Now if I calculate, if I try to plot this, so this is when T is equal to 0. When T is equal to 0, it is equal to K by T. So this is, maybe this is K by T. And when T is equal to infinite, it will be equal to 0. So it will be monotonically decaying expression for this. Now, if I put K is equal to 3 and T is equal to 2s, 2 seconds, it will be given like this. So it entirely depends on the value of K over here and capital T over here. So the response of this particular system is actually very, very crucial and it is dependent on the certain factors. Now consider step response. If I can calculate the step response, the similar thing I can do, I do partial fraction of this and I will try to segregate it and I will try to calculate. So this is the partial fraction I did. Now I will calculate the system response. So this is the forced response and this is the natural response which we are obtaining at when it is subjected to you can say other signals. Now if I calculate this, I can inverse Laplace transform. If I take, then I can write this, the time response of this particular system will be Kt ut 1 minus T. So if where ut is equal to 1, I can say, now again if you put the value of T is equal to 0 here, If t is equal to 0, the response is actually 0. And when t is equal to infinite, it will be equal to 1. So the maximum value of this type of system will be equal to reaching to 1. This is how we calculate. Now, some certain parameters we can actually calculate when this t is equal to t. So this t is equal to t, then this is equal to 0.632k. So here it will be reaching to k. Now, this thing we can say, we can see over here that 63% of the higher value we are actually achieving in this time. So this particular time is actually also having some importance when the DC values are actually reaching of the 63% of the steady state response. So this the DC gain is nothing but the steady state output by input. So it is equal to 10 by 1 over here. When I put k is equal to 10, t is equal to 1.5 second, then I can easily calculate it. So the expression of this will become 10 1 minus e to the power minus t divided by 1.5. So you put value of t is equal to 0, you will be getting this value. You put t is equal to 1.5, you will be getting this value. And you put t is equal to infinite, you will be getting this much value, that is 10. Likewise, you can see if I change the value of t over here, then the shape of this curve will be actually changing. That means the response, now what I can say, this response is actually, what this response is during this, before reaching the steady state, this part is transient period. So here you can see that if I'm changing the t, the response of the system, or maybe I say the transient response of the system, actually depends upon what it actually depends upon t, capital T. And capital T, if you remember what is capital T, capital T is nothing but, if you see, k1 plus, this was our transfer function. That means the t is actually the parameter which is actually deriving, which is actually indicating the pole. That's why the t is important. So here you can see there are 5 time constant like this when it is actually capital T, when the time is equal to 2t, when the time is equal to 3t, when time is equal to 4t and 5t. 5 time constant, and the value of the particular response is actually shown. So if you put small t is equal to capital T, then what will be happening? 1 minus e to the power minus 1 for first at t. Now at small t is equal to 2t, what you will do? Ct is, it will be equal to 1 minus e to the power minus 2t divided by, so 1 minus e square. Likewise 1 minus 1 upon e cube. Likewise 1 minus e to the power 4. So here you can say that at capital T, 63.2% of the 2% of the DC gain will be appearing in the transient response. That means during this transient period, the output response of the system when it is subjected to step input will be 63.2% of the DC gain. So it is a very important indicator. So if I just draw effect of DC gain, if I see, so you can say effect of DC gain over here, the transient characteristics is actually not changing, but you can see the the steady state error or steady state values. Here k is equal to 1, here k is equal to 3. The steady state response of this particular system is changing. So the DC gain actually affects steady state response. Now, when you see the step response of the first order system, and if I differentiate it with respect to time, I will be getting this kt e to the power minus t. That means it is impulse response of the, it is impulse response of the first order. So step response is this, impulse response is this. Now take one example. If you see the impulse response of a first order circuit is given below. Find out the time constant, DC gain, and the transfer function and the step response. So how you will do it? The Laplace transform of the impulse transform of the system is the actual transfer function of the system. Therefore, taking Laplace transform of this, I can do it by calculating this. So this 3 upon s plus 0.5 will be the transfer function of the system. And if I convert it into the standard form, I can easily write that response of the system or transfer function of the system will be this. So this will be the DC gain, and this will be the time constant. So the DC gain will be equal to 6, and the time constant will be equal to 2. Okay. From here I can write. If you can draw the step response in your notebook, it will be very easy for us. And if you take these things, and you can easily draw the step response of this. Now, for obtaining the step response, you will be able to integrate it. And you integrate it, and we can find that if the initial condition it is equal to 0, we can find out the value of the C over here, and C is equal to 6. So the impulse response will be given by this. So how we draw this? It is very easy. You just take this time axis t. Now put t is equal to 0. If t is equal to 0, then it will be equal to 0. When t is equal to infinite, it will be equal to 6. So it is between 6 and 0 and 6. So the step response will be like this. Now put t is equal to, you can say, 2. Yeah, or I can say 1 by 0.5. Now put t is equal to 1 by 2 into 0.5, and like this you can find out the intermediate value from t is equal to capital T, t is equal to 2t. Likewise, you can do it. Now, if initial conditions are not known, the partial fraction expansion is the best choice. So when it is subjected to a single step input, what I do, I multiply this step input with this. Now I will do the partial fraction. If I do the partial fraction, so over here, I can say that this 6 is equal to a into 2s plus 1 plus b into s. Now put s is equal to minus half. If I put s is equal to minus half, what I will getting? 6 is equal to b into minus 2. So this b is equal to minus 12 will be here. Now if b is equal to minus 12, just put this value in this. So b is equal to minus 12s. Now put s is equal to 0. If I put s is equal to 0 here, then what I will be getting? This a is equal to 6. So here you can say this b is equal to 12 and a is equal to 6. So over here I have written the smallest one, that means minus 12. So if I write this like this, this is a is equal to 6 by s minus 12 2s plus 1. So I calculated 6 by s minus 6 and s plus 0. Like this I have calculated. Now the impulse response of this or time response of this can be easily calculated from this. Now the ramp response of the system is actually also very important concern for us. I can do it. Now here I do the fraction. The ramp response can be given as this: t minus t, capital T into e to the power minus t. So this is how the ramp response when k is equal to 1 and t is equal to 1. So this part, which is actually unit ramp and ramp response, can be considered as the error. Now here also, when I take the value of k is equal to 1 and t is equal to 3, the error is shown as here. Now parabolic response, the parabolic response also we can calculate by using Laplace, and I leave it for you people to calculate it. Now, how we practically determine the transfer function of first order. So often it is not possible in practical problems and real applications to obtain a system transfer function analytically, but we can do it because the system is closed and the component parts are not easily identifiable. So the system step response can lead to a representation even though the inner construction is not known. So with a step input, we can measure the time constant and the steady state value from which the transfer function can be calculated. Now, practical determination of the transfer function of the first order system. Now, for example, we assume the unit step response is given and it is shown in the figure. So from the response, we can measure the time constant when the final value of 63% is actually reaching. Since the final value is about 0.72 in this particular response, we can say the time or we can say where the curve is reach 0.72. So here time is equal to 0.13 is actually you can say the time response of the circuit, and k is equal to 0.72 is the steady state value. So for determining the transfer function of this function, we can say 0.72, 0.13 s plus 1. This will be the transfer function. Like this I can write. Now, when it is having, when there is first order system which is having 0. So how 0 is defined? If the value of this particular transfer function 1 plus alpha s is equal to 0, so this s is equal to minus 1 alpha will be 0, and s is equal to minus 1 by t, it is equal to infinite. So this is the location of the 0 and this is the location of the pole. Now the step response of the system can be given as, if I multiply it by s, then what I will do the partial fraction. So if I do the partial fraction, it will be looking like this, and the system response, if I take, then it will be inverse Laplace transformation of this can be written by this. So this simply kt and alpha minus t e to the power minus t by 2. Now again you see that the transient response is actually depending on this capital T, which is nothing but the pole of the system, 1 by t, the pole of the system. So this transient response is actually dependent on this. Now without 0 also we can do, and with 0 also we can do. So if the value of this t is greater than alpha, the response will be the same, and it can be written as this. Now when t is greater than alpha, the system would look like, you can say, a unit response like this. When t is less than alpha, the unit step response of first order system will be like this. Now here you can say the effect of the 0 in the system, this is when t is less than alpha, when t is greater than alpha. So the value of the 0 is actually also important. If the value of this particular 0, the value of this alpha is less than t, if it is greater than t, then it is look like this. So the 0 presence of 0 in the transfer function is also actually highly affect the transient response or the steady state response of the system. Now if I just calculate without 0 and the 0 which is having less than pole value, 0 is having greater than alpha value, we can also calculate this. Now this you can do by yourself. Now we just see an example. A thermometer requires 1 minute to indicate 90% of the response to the input. Assuming the thermometer to be first order system, find the time constant. So if the thermometer placed in a bath and the temperature of which is changing linearly at a rate of 10 minutes, how much error does the thermometer show? Now, if you see that the DC gain of this is 10 s plus 1, CS 10 s plus 2, s plus 3, and you can see the comparison of this. Also, we are having first order system with the delays, and you can actually calculate the system response with the delay. So there will be some delay in the system, and you will be able to get this response. So first order system with the delay, here there is a delay in the system. So there will be, if you calculate this particular, so this delay is for 2 seconds, and then the response will be actually shooting up with reference to the step input. So there are some examples of the first order system like DC motor, which is where I've shown the transfer function of this. So you are having the value of KT, RA, B, KT, KB, RA, and you can actually simulate the DC motor. So this is very important part where you can actually armature control DC motor can be treated as first order system, which is having only DC gain, and transfer function like this and having one pole. So here we are having poles of this DC motor is equal to S is equal to minus B plus KT KB by RA divided by J. So this KT KB RA are the internal parameters or which are given over here. And this can be given and you can calculate the response, step response of the DC motor. Electrical system also, this we have done in lab also, where we can actually analyze this electrical system or maybe the filter of the system, where we are taking the output at the capacitor terminal. Likewise, you can do when you take the output at the resistance terminal also. So these are two different filters with a single configuration. That means at one end we are using, if we are taking output at one end, we will be using, you can say, we will be devising a high pass filter, and on other hand we are devising low pass filter. Here mechanical system also is the same, where I can say if I compare this KTS plus 1, so this here K is equal to 1 and the T capital time constant is equal to B by K. So this is how B, and this is K, spring constant, and there is some piston values over there. So the response of the system when input is maybe you say ramp input or maybe you say step input is applied on that, the response of this particular system will be like this. So this is how we can actually analyze the examples of first order system. So with this, this presentation is over. If you are having any doubt, you can